Okay, so this is the first part of complex numbers on basic properties of complex numbers and also how to solve equations. Now that a lot of the geometric part of this topic on complex numbers has been removed under the new syllabus, a lot of the focus on questions in this topic are going to be on solving equations. So the first thing you need to know is that we typically represent a complex number using one of two notations. The ones that are most commonly used are the letter Z and the letter W. Some questions will also give the Greek letter omega to represent a complex number. But this is just for your background info that these are the three main notations used for, uh, or rather the three main variables used to denote a complex number. Okay, but the question will always explicitly tell you which variable represents a real number, which variable represents a complex number. Okay, so in general, a complex number z can be represented in Cartesian form x plus yi, where I is the square root of -1 and is therefore an imaginary number. And x and y are real numbers. So this is the Cartesian form of a complex number, and it is the only form that you are required to know under your new syllabus. In the past, students were also required to know the polar form, which was used mainly to express your complex numbers in the Argand diagram. Now, Argand diagram is still in your syllabus, but right now the only properties of Argand diagram that you are supposed to know is some very basic transformations and also how to plot points on the Argand diagram, obviously. But it's very simple because it's more or less just the same as the xy coordinate plane that you're used to. But more on that later. So that's the Cartesian form of a complex number. And you also need to know how to tell if two complex numbers are equal. So in general, there's a very important property pertaining to the equality of a complex number. That's, let's say, we could let a complex number z1 be x1 plus y1i, and let a second complex number z2 be equals to x2 plus y2i. Then in this case, right, we can equate these and say that z1 and z2 are equal if and only if x1 equals to x2 and y1 is also equals to y2. Okay, so remember x and y are real numbers, all right? And in addition, you also need to know about the conjugate of a complex number. So the conjugate of a complex number z is denoted by this notation. Z star is a little asterisk at the corner, and there are a few properties that you need to know regarding the conjugate. Okay, firstly is the fact that if you have the conjugate of a conjugate, that is to say z star star, you will just get z. And also, if you have the complex number z multiplied by its conjugate, you are going to get mod z squared. What is mod z? Mod z is the modulus of a complex number, which we'll get into in the next video on modulus and argument where we're doing Argand diagram. And in addition, if you have z raised to a constant n, so n is a constant here, and then you take the conjugate of this, it is the same thing as taking z conjugate to the nth power. So these are the three main properties of the conjugates that you need to know. But what exactly is the conjugate? In simple terms, if we go back to our Cartesian form, if basically, okay, if z is equals to x plus minus yi, then in that case, z conjugate is going to be this sign flipped. So if, let's say, z is x plus yi, z conjugate will be x minus yi. Likewise, conversely, if z is x minus yi, then z conjugate is equals to x plus yi. So any two pairs of conjugate complex numbers are always conjugates of each other. That's why I have the property on top here, that the conjugate of the conjugate is just the number. Okay, so that is nice and good. And another important skill, there's a lot of important skills in this topic that are best illustrated through examples lah. So first you need to know how to solve linear equations in complex numbers. And this is best illustrated using example 6 in your lecture notes. So this example 6 is on page 9 of your lecture notes, and it asks you to find the complex number z such that this equation is satisfied. So this is example 6 on page 9 once again. And I'm going to use this to introduce to you the skill that you will be using throughout this topic on complex numbers. So this is the question, and we're going to try to work from here now, okay? So the strategy in this case is to make z the subject. So how do I make z the subject? Obviously, I will have to cross multiply, right? So I will get z is equals to minus 1 plus I times 1 minus z. And important thing about complex numbers is that the normal algebraic rules that you learn in lower sets still apply. So the distributive law just applies. You can just expand it normally like any normal real number. Okay, and now here is the part, right? In order to compare real and imaginary parts, I want to group the terms containing z. Okay, so how do I do this? Let's look at what I have here, okay? Which parts of this contain z? This term and this term contain z, right? So from here, you can see that because I have z on this side, then I have z here, then I have minus iz here. So I can shift this minus iz to this side, such that this becomes positive iz, and then on the right hand side, it's still minus 1 plus I. So I make z the subject. You see here, it's pretty much the same types of strategies that you have been using for linear equations all along since Z1. Okay, and therefore you can actually simplify it, because in this case, right, let's compare the real and imaginary parts here. Over here, iz is obviously imaginary. That's on the left hand side. On the right hand side, minus 1 is real, I is imaginary. So later on, I will show you the more commonly used method in questions involving complex numbers, where you let z equals to x plus yi. So you express z in its Cartesian form. But in this particular very simple example, it's not needed. So basically, you can just divide across by I. You see? And therefore, I can simplify this. Now, how do I simplify a fraction like this? You remember in Sec 3, you learn how to simplify a fraction where a surd is in the denominator, right? How do you do that? You multiply the surd by its conjugate. So it's a very similar process here. I'm going to show you now. So I keep the original thing. And then you remember, in Sec 3, when we first learned this using surds, if I want to take the surd out of the denominator, I multiply of it by the conjugate over the conjugate. So that it's just 1. So in this case, my complex number is I, right? What's the conjugate of I? Conjugate of I, we explored earlier, is just minus I. So I just types minus I over minus I. And you see that because this is just 1, the value is the same. But because I times minus I, what is I times minus I? It's just 1, right? Because I is root minus 1. And then minus I is minus root minus 1. So obviously, this times this is just going to be equals to 1. So just like how when you have a surd that's an irrational number, like how root 2 times root 2 is just 2, you have irrational become rational. Likewise, if you have two imaginary numbers, or rather imaginary numbers that are the conjugate of each other, if you multiply them together, you will always get a real number. So it's just minus 1 plus I minus I. So it's just going to be No, sorry about that. It's minus I into minus 1 plus I. And another important property here to note, okay, I have minus I here and then I have I here, right? So I will get minus I times I, which is obviously, we know it's going to be minus I squared. Now think about it, what is I squared? Because I is root minus 1, right? So I squared is just minus 1. This property will be a very, very useful shortcut throughout this topic of complex numbers. Okay? So as a result, I am just going to get uh then minus I times minus 1 is just going to be I, obviously. And then because this is minus I squared, so this is minus minus 1. So it's just I plus 1. That's all. That's how I solve for Z. Now, I mentioned earlier that the more common method that we use in this topic on complex numbers is to let Z be equals to x plus yi and express it in Cartesian form. I think the next few examples will illustrate that better, but this is just solving linear equations. Just an introduction to get you all to see how we manipulate algebra with regards to complex numbers. But I must warn, okay, questions that are this simple almost never come up in A level. The types of questions that you should be used to are the ones that I'm going to show you now, which is solving simultaneous equations, uh, or you can also have the reverse. Instead of I find complex numbers that satisfy the equation, I can also find real numbers that satisfy the equation. So these next two examples are going to illustrate that, okay? We're going to move on to example 7 now. So that was example 6 on page 9. Now we're going to move on to example 7 on page 10. So example 7 on page 10 is simultaneous equations. And we're going to see how we solve simultaneous equations involving complex numbers. Okay, so in this case, I and W are complex numbers, and these are the simultaneous equations that they give you. So obviously, we know from what we've been studying since Sec 2 that when you are given a system of simultaneous equations, two things that you can do. One is substitution and one is elimination. As you progress through Sec 3, Sec 4, J1, presumably, I hope you have mastered this last year in J1. When you are just given a simple set of two simultaneous equations or even three simultaneous equations, now that you have a GC, please don't go and solve it algebraically. If the question does not explicitly tell you that you cannot use your GC, please just use your PriceMelt2 app, your polynomial simultaneous equation solver app to solve. Okay? But in this case, for complex numbers, there is unfortunately no app on your GC that allows you to just key in and solve. So this one, I'm sorry, you still need to revive your lower sec methods of solving by algebra lah. So I'm going to show you how to solve by substitution. If you look at your lecture notes, it will also show you how to solve by elimination. But as I'm sure you have also been told a long, long time ago in Sec 2, substitution is almost always faster, easier, and more straightforward. So I'm just going to show you substitution. Okay, it works the exact same way as with real numbers. So I have these two equations, right? Let's label them, okay? Let this be equation 1, let this be equation 2. So if I have, I'm going to work from equation 2, okay? So let this be equation 2. Now, if I have 1 minus 3i z plus w equals to 5 plus 4i. So in this case, they are very tame already. They've saved us a bit of manipulation by allowing both our unknowns to be on one side. So what we are supposed to do is we're going to try to express one of the unknowns in terms of the other. So obviously in this case, because w is alone, there's no coefficient, it's a lot easier to try to express z, or rather to try to isolate w on one side and then express w in terms of z. So if we move w to one side, we will get w equals to 5 plus 4i and then minus 1 minus 3i z. And we can simplify this a bit to give us this. Remember, distributive law still applies, so just multiply in, which will give us this. So let this be, actually I'm going to use a different color. Let this be equation 3. Okay, so let this be equation 3. And let us substitute, this equation 3 into equation 1. Okay, so if I do that, then I will have 2z, I copy equation 1 over, right? Plus I, but I replace w with like that. So I just copy this entire thing over. I sincerely hope this method is familiar to you. Maybe you haven't used it in some time. The full algebraic rigor in some time because you've been too used to pressing calculator. So hopefully, I'm reteaching you a bit of Sec 2 math, which you will unfortunately need to reapply in this topic lah. And this will obviously be equals to, copy over the right hand side of equation 1, 1 plus 2i. Okay, so I can proceed to simplify. In this case, I've expanded, but come to think of it, it's actually easier to leave it in the factorized form. So if you don't want to expand this thing, if you prefer to leave it in factorized form, that is okay as well. But I'm just going to go ahead here, and I'm going to start to expand and simplify. Now, I times I is just going to be I squared. So what's 4i squared? I squared is -1, right? So this is just going to be -4. Okay, keep that in mind. And we can continue expanding. Once again here, I times I. So this is going to be 3i squared z. So because I squared is -1, this is just going to be minus 3z. And then the right hand side is unchanged. So you notice all my unknowns, all my complex numbers are on the, no, actually the right hand side still has an imaginary part, but it's just that all my unknowns are on my left hand side. So if you try to factorize the z out, you will end up getting this. No, it's minus. So I want to factorize the z terms out, right? So there's going to be minus 3 plus I z minus 4 plus 5i equals to 1 plus 2i. So now I'm going to move everything that is not z over to the other side. So I will end up getting this. So I move this term, this term, this term to the other side. I will get 5 minus 3i, and then I will just divide across to get this fraction. Now, once again, this is very similar to what we have actually done earlier. Earlier on, I showed you how to multiply by the conjugate, right? But actually, there is a method on your GC, on your TI-84, that allows you just evaluate the conjugate of a complex number. Let me see if I can show it to you now on the online TI-84. Okay, so first I need to be able to change the mode to complex. Okay, so instead of real here, I'm going to go down a plus bi here. I'm going to select this, and that will change it to complex. So I just check on top. Here it says a plus bi, and if you see, if I key in, I should be able to get I lah. So basically, if I want to evaluate this particular fraction, 5 minus 3i over minus 1 minus I. So I'm going to try to key that in now. And you can see that if I key that into the GC, it will automatically simplify this for me. That is going to get minus 1 plus 4i. So you need to, once again, make sure that you go to mode, make sure that this thing on top over here says a plus bi. And by the way, how you key in the complex number I in your GC, right? If you just go to second, and then you see on the decimal point here, there's an I. Click on this, and that's how you key in I. So you just key in your fraction, press enter, and then it will automatically simplify for you. So on top, I show you how to do this manually by multiplying by the conjugate. But in this case, because the fraction is a bit more complex, you can make your life a lot easier. So z is just going to be equals to minus 1 plus 4i. Okay, so this is one of my solutions for z. Now, I can sub this back into equation 2 or equation 3. But I'm just going to sub this back into equation 2. So I'm going to sub back into, what was my equation 2? 1 minus 3i z plus w equals to 5 plus 4i. So 1 minus 3i. Then I'm going to replace z with minus 1 plus 4i. So I'm going to sub this in, and then plus w equals 5 plus 4i. So once again, this is from equation 2. Okay, and so therefore w is just going to be equals to 5 plus 4i. I move these terms to the other side, so minus, and this is a product, so it's actually just one term. And if you expand and simplify further, I will show you how to expand and simplify further lah. But once again, it's just distributive law, nothing that's deep. But here we come, right? Minus 3i times 4i, so it's minus 12i squared, right? What's I squared? Minus 1, so this will just become plus 12. So if you simplify further, you will get w is minus 6 minus 3i. I'm sorry if that was a bit lost, but that is basically an introduction to how you solve simultaneous equations involving complex numbers. Okay, take your time to understand, because after this, we are going to go on to the other type of simultaneous equation. Okay, so this particular example 7, has showed you how to solve if they want you to find complex numbers that satisfy an equation. But they can also give you, I wouldn't say it's a reverse type of question, but it's certainly another type of question that they can give you for simultaneous equations. And instead of ask you to find complex numbers, they can ask you to find the real numbers that satisfy an equation. So this one will need slightly different. We're going to look at example 8 in your lecture notes now. That's on page 11. Now, I don't like how succinct the explanation or rather the work solutions in the notes are for example 8. So I'm going to show you my way of doing it, okay? So in this example, we are going to make use of the property of equality of complex numbers, where complex numbers are equal if x1 equals to x2 and y1 equals to y2. So we're going to do that now, okay? Example 8 asks you to find the real numbers a and b such that, actually this is not a simultaneous equation, it's just one equation. So I think that's why it's very worth showing you how to do this, okay? Because a lot of students, when they see, how can I have one equation but I have two unknowns? So this example, I will finally be able to show you my favorite scale and also the most important scale in this topic of complex numbers, comparing real and imaginary parts. Okay, this skill is very, very important, so please put your head up. Let us solve this, okay? So, we are given this equation, and the first thing to do is, once again, I'm trying to get rid of the complex number in the denominator, right? But in this case, I cannot just go over to my TI-84 because my TI-84 only lets you evaluate if you know what is on top and what is on bottom. This one, my numerator and my numerator A and B are unknown. So I have to do it the manual way. That's why you also need to learn the manual way. There are a lot of things I hope you realize by now in H2 Math. Got manual method, got GC method. You need to know both. Because even if the GC method is faster, more efficient, you've gotten used to it, sometimes the question can start with the dreaded line, do not use a calculator in solving this question, and then you suddenly get stuck. People got asked before, even if they say cannot use calculator, how will they be able to tell that you got use calculator or not? Answer is, if the question explicitly say do not use calculator, means that the method mark will have method marks for solving it the manual algebraic way. So if you don't show your intermediate steps, then the examiner will know, aha, you didn't pay attention to the instruction, you go and use calculator. That's why even if you get the correct answer, they will not award you any method marks. Okay, so please know the calculator method, but also know the algebraic method. Okay, so back to the question. I'm going to get rid of the denominator of the complex number in the denominator by multiplying it by the conjugate. So I'm going to do this for both the fractions. Okay, I'm going to color code this, and I'm going to color code this. Okay, now what is the conjugate of 1 plus I? It is 1 minus I. Settled. That's one term. Next, my denominator is 2 plus I, right? What is the conjugate of 2 plus I? It's just 2 minus I. And then the right hand side is unchanged. Okay? So if I simplify this, 1 plus I, 1 minus I, you can simplify yourself if you want, but I'm going to tell you it's just 2. Okay? If you want to convince yourself, you can do the expansion manually. But basically, you just need to remember I times minus I will get minus I squared. I squared is minus 1, so minus I squared is just plus 1. So you get 1 plus 1, 2. Okay? And then in this case, I have 2 plus I times 2 minus I. So once again, I times minus I is just 1. 2 times 2 is 4. So 4 plus 1, 5. Done. You don't even need to expand manually. You should be able to see it quite intuitively. If you just remember that I squared equals minus 1, therefore minus I squared is just 1. Okay? Please remember that property that I squared is minus 1. Don't be stupid. Okay? And once you get this, then obviously you should be able to see by now that the way to do this is by partial fractions. So I'm going to try to split this. Actually, to call it partial fractions is wrong lah, because you don't actually need partial fractions. It's just in this case, it's just a over 2 times 1 minus I, right? And then b over 5 times 2 minus I. So this is where we start to compare real and imaginary parts. Okay, so if I compare real and imaginary parts, I'm going to try, because my right hand side is already nicely in Cartesian form, what? Real number minus real number I. So my role here is to try to get my left hand side in this very neat Cartesian form also. So I am going to express it like this, okay? My real parts all go to one side. So in this case, just a over 2 plus, in this case, is 2b over 5. So you see how this term is my real term, right? And then my imaginary term. So I want to factorize I out. So in this case, because there's a minus here, it's just minus a over 2I plus b over 5I. So I factorize I out from these two terms. And ta-da, on my left hand side is now also in Cartesian form. So from here, this is where you learn your $1,000,000 scale to compare real and imaginary parts. Okay, so if you compare real and imaginary parts, you just see that it matches directly what? A over 2 plus 2b over 5 equals to 7 over 5. Minus a over 2 plus b over 5 equals to minus 4 over 5. Question never say cannot use GC. So at this point, please just use your polynomial simultaneous equation solver to add on your GC. In case you've forgotten where that is, okay, it's just here, apps. Okay, this online TI-84 doesn't have the app for whatever reason. But yeah, it should be on here on your GC, like just you click on apps and then I think polynomial simultaneous equation solver 2 is number 4 in the list should be. Okay, yeah. Technically, can the question kill you by adding a line on top, do not use GC, such that they force you to solve this algebraically? Yes. But I'm not going to show you how to do that because you should be able to know how to solve simple things like this in Sec 2 because A and B are both real and constants. So just using GC, A equals 2, B equals to 1. Press your own GC and figure that out yourself. And that is my final answer. Okay, so I'm sorry if this was a bit of a heavy introduction, but I hope through these 3 examples I have shown you how to perform algebraic manipulation using complex numbers, how to compare real and imaginary parts, very, very important, and most importantly, how to solve simultaneous equations involving complex numbers. So this is one half of the algebraic heavy questions that they can set you in complex numbers. The next half that we're going to explore in the next video, I'm going to come over to the right hand side of my board here, is going to be on solving polynomial equations involving complex unknowns.